This video is to look at the derivation of the equations of motion for constant acceleration in kinematics. Notice first of all the condition on this. This is only true if the object is undergoing a constant acceleration. If you were in a situation where it weren't, you would have to use another technique, such as breaking it into sections, or having to consider it on a larger scale if it was something like a changing gravitational field. So these equations link together the 5 main quantities for kinematics that we've been dealing with: the displacement of an object, its initial and final velocities, its acceleration, and the amount of time that has gone by. How we're going to do this is we are going to use velocity time graphs as a way to show where these equations come from. So I'm going to consider some object that has a speed that is increasing. So I'm going to draw a velocity time graph here, where the object starts with some positive initial velocity and then has some acceleration to some faster final velocity in the positive direction. So maybe it gets to here, and here's its final velocity, more or less, in some amount of time that has gone by. So we talked previously about how the slope of a VT graph is the acceleration of the object. And you can convince yourself of that if you consider the units of the slope. Not the quantities themselves, but the units of them. So on the rise, they're both velocities, so my units are meters per second, and on the run, my unit is seconds. So I get a unit of meters per second squared. And that's going to be true of any graph. Thinking about what the units of these quantities will be, such as the slope and the area under the curve, will help you know what those represent. So if I then think about the symbols, the actual slope, not the units. My rise, I ended at some final velocity. Subtract starting at some initial velocity. So the change in y over the change in x, I ended at some time t. I started at t equals 0, just for the sake of simplicity. And then I'm going to rewrite it without the 0. Now I'm going to simplify this. I'm going to multiply both sides by t to get it out of the denominator. Vf minus Vi. And then I'm going to bring Vi to the other side. So here's my first equation of motion for constant acceleration. Now I'm going to do the same process with the other key feature of a graph, that being the area underneath. So it helps to think about this, because it's an odd shape, as being divided into a rectangle on the bottom there, and then a triangle sitting above it. So we talked before about how the area under is the displacement. And again, you could convince yourself of this with the units. If I think about that rectangle, I have a unit on the height that is in meters per second, and my unit along the base is in seconds. Those cancel, leaving me with meters. So I'm going to do the same thing where I use these general symbols. I'm going to just draw this to remind myself I have to deal with the rectangle and I have to deal with the triangle. So my rectangle is easy. It has a height of Vi and a base of t. And my triangle, my formula for the area of a triangle, 1/2 times the base times the height. And like the slope from last time, this is going to be Vf minus Vi. Then I'm going to simplify this. A math teacher would not like this because I have two different terms that have VI in them, and I can make this a lot more simple of an expression if I combine like terms. So I'm going to start by expanding my 1/2 t. I'm going to expand and distribute to the VF and the VI. 1/2 VFT minus 1/2 VIT. Then I'm going to combine my first and third term there just to make them nice and simple. And then how physicists usually write this is to factor out the 2 and the t. I'm just going to slide over to my left-hand side here. D equals VF plus VI over 2 times t. This gives me equation number 2. And you may also recognize VF plus VI over 2 as the average velocity. Now, how I get the next ones are just by combining these two. So for the first one, I solved the second one I just came up with for VF and set it equal to number 1 and solve this for D. So here's the one I just finished. Apparently my computer is picking up every piece of my hand as I write on my screen here. I'm going to bring the 2 up. I'm going to multiply both sides by 2. I'm going to divide both sides by t because I'm trying to solve for v here to get started. And then I'm going to bring vi over to the other side. Now this looks kind of messy and kind of gross and kind of like something I would not like to work with, but just remember this is only a step to getting the next equation. This isn't actually a new equation. So I solved for v, and now I'm setting it equal to number 1. Number 1 was VF equals VI plus AT. Set that equal to what I just did over on the left. And then I'm going to simplify that because, again, there are 2 VIs, and a math teacher would say this is not in its proper form. So I'll bring the minus VI from the right over to the left. So I have 2 VI plus AT equals 2D over T. I will multiply both sides by T. And I will divide both sides by 2. And this gives you the third equation. I'm not going to derive the 4th and 5th ones, but if you are interested in doing that yourself, here are the instructions. For the 4th one, you consider that area under as the large rectangle VF minus the upper triangle. So instead of doing this underneath piece this way, you consider this whole rectangle and then subtract this triangle, and you'll come up with the 4th equation. And then for the 5th one, you take the very first one, solve it for t, and plug it back into number 3. Where that leaves you is with these 5 equations. Now you might be wondering, why do we need all 5 of these? What is the point of having each one? And the reality of that is that each one has and is missing different quantities. So for example here, that top one there, it has VF, it has VI, it has A, and it has T. This equation would not be useful if I was given the displacement or if that was what I was trying to find. Similarly, the second one has D, VI, VF, and T, but does not involve acceleration. And I can keep going here and check off what each of these equations does and does not include. You can see that I have 5 because each one is missing or has eliminated one of the kinematics quantities. So which equation I'm going to use to solve a problem is very much dependent on what information do I know and what do I not know. In the next video, I'll show you a couple of examples of using these and how I go through my process of knowing which one to choose.